Um, but for this problem, you can indeed use binary search. But how can you formulate the problem in the first place in order to use binary search? I think that's the much trickier part. As you get more comfortable with writing binary search, writing the binary search isn't the tricky part. It's coming up with how to formulate the problem. And this is an example of how to do that. So let's think about going back to what if data was sorted, right? Just not this problem, but a different problem of just finding something in an array that's sorted. What do we get to do each time? Why does binary search fit that pattern of sorted data? Well, it's because we always have a binary search, right? You always have a low and a high bound, and you always cut the search space in half, right? One interesting variation of that idea is this problem. The key part being you can return any of the peaks. It's not so much that there's no solution on the side you crossed out. It's that you can find a side that has a solution, right? It's possible that when you use binary search, both sides have a solution. But as long as you can cut down the search space and get closer and closer and have the amount of work you need to do each time, binary search is still valid. So even though this side might work, you can also just cross it out if you can guarantee for sure that there's going to be an answer on the left-hand side of the problem. And this is what this problem really illustrates. I have the pre-baked stuff that you might expect. So the first thing to get right is the bounds, right? For an array, it's a bit easier when you're searching through something. So the low is going to be 0, right? The high is going to be the max index, same as before. This I'm going to use as my best candidate, is my peak. I'm going to initialize that to low right here. And then I'm going to go through like usual. I'm just going to find the midpoint. And actually, to help visualize, maybe it's better that I print things out. So I've drawn these peaks, for example 2, because I think that is the example that I care most about here. Hopefully it'll convince you that this stuff works. So I'm given this array of numbers, and this is how it's shaped, right? I cut the mid, so I get the mid by cutting the space in half, and I compare the middle value, just like in a normal binary search. What I do is really, this is the key comparison. Is the value of the index right now greater than the value to the left of it? That's all I care about. And this part right here, that's just to guard the fact that like if I access a value in the array that's like less, like with an index less than 0, that's going to give me an error. So that's all that really is. The key part is to keep in mind just this part of the comparison. You can see that this is how the invariant works. So I'm at 3, right? And this is right here, right? Mid index is right here. And with this 3, I'm saying, oh, hey, 3, I'm not going to compare to a target value or anything, right? What I'm going to compare against, actually, very interestingly, is just this 1, right? Is 3 greater than this 1? Because if it is, right, 3 is possibly maybe a peak. I don't know what's on the right-hand side, but it's possibly a peak. I don't know what's on the right. And what I can do is, well, I know 3 is greater than something, right? So there has to be a peak on the right-hand side. So that's how I make the decision to cut the left half. I don't need the left half anymore. because 3 is greater than something. So there's only two possibilities, right? Something is greater than 3, or 3 is a peak. That's why I cut the left half. I don't need it anymore. I only care about stuff on the right half now. Okay? So that's the key idea here. So now what happens is I'm going to record this, right? This is how I tend to use it. You can write a 3-branch binary search if you want, but I have this habit that I just record the value, the closest value that I found so far, and I just keep doing that. So I record the best guess that I have so far. It's either going to be 3 or it's going to be something else, and it's going to be at this index. Okay, so the next iteration, what happens? Low is now at 4, right? Index 4. So I move the low bound up here, right? Because I crossed out this side of the problem, and high is right here. Right? This is my low, this is my high. The mid is going to be at index 5, so I'm looking at 6, right? So 6, I do the same thing, right? 6 is actually greater than an element on the left side. So either 6 is a peak, or there's going to be something greater than 6 to the right side, right? And remember, the edge of the array is at, we can assume, is negative infinity as specified by the problem. So I cut the left side again, right? Notice anything could have happened, right? There could have been a peak right here. Like the problem could have gone this way, right? Maybe there would have been more numbers, right? But it's okay to do this because as long as you have an invariant, as long as you guarantee that the half of the problem that you choose always has an answer, you get to cut that answer in half. I mean, you get to cut the space in half. And that's why binary search works here. So this problem actually passes all test cases, but I'll show you that hey, what happens next, right? So eventually low is at index 6 and high is at index 6, right? What happens, we find 4. 4 is not greater than the number to its left, right? Because 4 is comparing to 6. That's not true. We don't record this value. And in fact, when we have high equals mid minus 1, next time it's going to be 6 and 5, right? But that violates our condition for the while loop. We exit out with the best recorded value that we have. So that's find peak element. So yeah, hopefully that shows you that binary search, as long as you can find an invariant for using binary search, you don't need the data to be sorted. Keep in. The invariant is that is actually this is the condition that I hold. I am always going to choose a search space where there is going to be a peak, essentially. Right, the mid must be greater than just the value to its left. And that allows you to actually create the situation where every low and high bound now, you're guaranteed to have a peak. As long as you guarantee that you're picking values that the current value is maybe greater than to its left, then you know that the solution must exist on the right-hand side. Now, if this isn't true, right? What if this isn't true, right? You have something that goes like this. You have a downward slope like that. You actually know that the peak must be on the left, right? If you have a slope that looks like this, you know that a peak must exist on the left. That's kind of it's kind of the key intuition to this. You just make sure that whichever side you're picking has a peak. And a peak will always be on the side with an element that is greater than the mid, or equal to, I guess. Now you could technically flip around some of these signs, right, and do it that way. There's other ways to write this type of invariant, and you can see that on other people's solutions. Some people use this invariant, right, where basically like this number has got to have like this situation going on. I don't know, I didn't like read through this, but they have they have a bunch of extra conditions that they do at the end. And don't be surprised if like you find yourself doing this in some binary search problems. It's actually like hard to get the indices right. I'm probably sure that I had to like rewrite this at least a few times in order to get this down into just, you know, shorter code, which isn't always the best, right? So look through some of the invariants if you're interested. Other people like break this down into like a different condition. They branch differently than I do, but each time it's like a binary search, and all they're doing, right, just keep in mind that there's going to be an answer either on the left or the right side, and you're just picking how you're going to find which side to use. This part makes the most sense to me, so that's why I picked it. Any other questions? This is probably a question that you'll probably want to do on your own, just to have it sink in. Thanks so much for coming, Spencer. All right, take care. Okay, cool. Take care. All right, so I know it is 1. I'm just gonna summarize a bit, and then we have time to like work on stuff if you're able to. Sorry I was slow this time, again. So here's some essential patterns and how you recognize this type of problem. In general, there's going to be a key invariant, and it's if you can find a way where the answer can be maintained by cutting the search space in half, it's a good candidate for using binary search. We saw this in find peak element, but to be honest, most of the times when you look at problems, you're going to be looking at how things are sorted, right? Because sortedness is one way to have that invariant, right? Binary search for an element in an array works because sortedness gives us an invariant to use. That invariant that is preserved is the fact that elements greater than the mid are all going to be greater than the mid, right? And the elements less than the mid are always going to be less than the mid. So this allows us to cut that search space in half. That's why binary search works for finding elements in an array, right? So when you're searching for an item in an array, it might be worthwhile to consider if you can sort it first. There's a cost for sorting. In general, that's going to be n log n time complexity, but it might be worth it if you're going to be doing repeated queries on data, right? So keep that in mind. There's also synergies between other types of algorithm patterns. We're not going to see too much of these today. One of them is creating your own pieces of data when you do some problems and doing prefix summations. And if all the elements are less than 0, right, if you are doing something where you have an array of like numbers, and if you look at the prefix sums, well, this is 3, this is 4, this is going to be 7, right? Because each time I'm just adding the element, right, to what I had previously. You might be able to use some of this stuff, right, be able to create an array for yourself in order to use binary search. In fact, this is one of the key insights that we're not going to go over because it's the longest increasing subsequence and we don't have time to do that one. But this also synergizes anytime you have derived data or sorted data, all right? If there's no invariant, you can create one yourself, sometimes for the problem. We're also not going to see this, but as you saw before, an idea about binary search is this trial and error, right? You can take this idea further and not use binary search over indices, but actually use it over a solution space for optimizing. As long as you have a fast check function, you can usually solve the problem very quickly, right? And this is what makes it better than dynamic programming problems. Again, this is too much material to cover in one lecture, and we're not going to do that today. With that, we're ready for some small group work. If you have time, this problem is search in a rotated sorted array. So first of all, I'm not going to keep you here, obviously, if you have other obligations. So are both of you willing to try this problem? If not, I can wrap this up. Okay, that's good. Okay. All right, so there's a Google Doc that I put on with the problem template. Search and rotated array. Here I can just copy and paste that problem into the Discord chat. And feel free to read through that. And I'll give you a minute to do that. And then I'll have my screen up, but also be hopping into the Google Doc to help you out while you code. Yeah, you can copy and paste it. Whoops, that was a lot of stuff I just pasted. Whoops. Okay, I might have to tab this around a bit. Okay, do people feel like they know what the problem statement is? Yeah, so let me clarify a bit for this. So, and if you have any questions, I'll watch the chat. So just feel free to interrupt me if you want. So this is search in a rotated array. What's interesting about this problem is different from just searching through something. The values are sorted, but it's rotated, right? So if you look at this, right, it's 0, 1, 2, but then it loops back around to the first index, and now you have 4, 5, 6, 7. Okay, so you can think of this as like rotated 1, 2, 3, 4 spots, right? Because if it was not rotated, the 0 would be at index 0, right? But here, the index 0, the value 0 is at index 5, right? 0, 1, 2, 3. Now it's at index 4, right? And like in a classic binary search problem, what we just want to return is we want to return the index of target. So our target being 0, we want to return index 4. So our target in example 2 is 3, and it doesn't exist, so we want to return -1. So if we wanted to find a target of, let's say, 4, we would output 0 in example 1. So that's basically the problem statement. We're basically doing a search, and we want to return the index. One complication is that the array is rotated. Additionally, we must write an algorithm with log n runtime complexity. So that should immediately help us think about binary search. Also, the fact that it's a little bit sorted, but just rotated, might also help us. So there's a key and thing to maybe think about. What if we could just find where the pivot index was first, right? What do I mean by pivot? I mean the smallest value in the array, right? Because if we could find the smallest value in the array, then basically we would basically know what the two halves are, right? We could then take target and we could binary search either through this half or we could find it in this half. And we know how to do that, right? We could just use bisect in that case, right? So the key part of the problem that I want to start off thinking about is, maybe guide this a little bit, is can we find the pivot point in log n time? So this low right here, we want to, so I'm looking at this and I think, so if low is 4, you're probably thinking about binary searching starting from here. And we will do that. We will do that for this particular problem. But in order to figure out that we should start the low at 4, we want to find out how far this array has been rotated. And we do that by finding the pivot index, right? Which is going to be the index of the smallest element first. Does it make sense why we need to do that first before binary searching for the actual target value? Right, because the pivot point, we can use that as the low. We can use that to help us find what the low and high are, right? Because you can imagine if you were looking for 7, right? Well, you may or may not find it with just a normal binary search, right? Because if everything is rotated, you don't have the invariant that you're looking for, because you go up, but then you go down, right? Well, you start from a lower point technically, right? That's how the values look, right? 4, 5, 6, 7, right? They're sorted, but then suddenly you go from 0, 1, 2, right? So you can binary search later after you find the pivot index. So we want to find out the pivot index first. That can tell us what our low and our high bounds are, right? Because once we look for 7, we don't want to look for 7 starting at this index, right? Starting at index 4 all the way to here. We want to look for 7 on this half. So the strategy I'm thinking about is first, right? Find pivot, and then pick which half, and then finally binary search on the half we want. The index of 0 would be the pivot point, but that only works for this problem, right? So we have to do that more generally for any input, any kind of array that's passed in that fits the problem constraints. So in a different... Go ahead. We can represent the pivot by something called k, sure. How do we find k? That's the first part of the problem. Yep, basically. How do we write code to find the pivot? We are going to probably use a while loop. It's going to be... Okay, so let me address two things first. Ethan said, we can find the pivot by incrementing until the next element is less than the previous element. And I think that's a really good insight, right? So what this proposes, well, let me formulate this in two ways. What if we just started from the left end of the array and one by one looked at the previous element that we saw before, right? Obviously, the first index is going to be a special case. 4 is not going to be necessarily, there's nothing to the left of 4, right? The 5 has something to the left, and it is greater than 4, right? 6 is greater than 5, 7 is greater than 6. 0, however, violates that pattern, so we know that this must be the min, right? So this is how you find the pivot index, right? This is one way to do that. However, from how I've described it, this would be a linear search, right? And that violates this constraint of the problem. You must write an algorithm with log n time complexity. So that's like a major hint. To find the pivot, like, I think Ethan's onto something, right? We do increment until the next element is less than the previous element. But we don't necessarily need to do that type of logic in a linear search. We can use binary search in order to try and do that. Okay? So finding the pivot, I'm going to claim we can write a binary search in order to do that. Right, so to start off the binary search, let's define our left bound and our right bound. So I think this low, instead of being 4 right here, if we're going to find the pivot, we can change that to 0. And this high, because we're looking for a pivot and the pivot is guaranteed to be in the array, the high is actually length of nums minus 1, because we're dealing with indices. Okay, so now we start our while loop. if we follow the template, what kind of condition are we looking at? Yep, it's low less than or equal to then high. And we'll want to calculate our mid. How are we going to do that? So we're going to establish an invariant, right? That's a great time for that question because we're going to go over what invariant that we're going to use. We're able to use binary search because just like with find peak element, you can always find the side that is going to have an answer for you, and you get to throw away the rest of the elements that are not going to be where the answer is. And to speed this up, and to be honest, because I haven't worked in this problem for a little bit, I'm gonna scooch this a little bit over. Yeah, so I did a 3-branch variation. What I do is I compare the value at mid, and I compare that to the right end of the array. And if the value from the midpoint, right, let's say this is 7, is greater than the right end of the array, then I know that the pivot cannot exist on the left side, right? Because when you deal with a rotation, you're always going to be dealing with potentially 2 sides, right? There might be the case where it's no rotation, but that should also be handled by the binary search itself. So the key invariant to realize is let's say I have the mid, but there's also the value at high, right? And this is low. So if I grab this value in the array, and I know that let's say this is x. If I know x is greater than nums high, then I know that the pivot index cannot be on this side at all. Actually, I'm going to call this, I'm just going to call this value. X is confusing because I draw out x's a lot. So I know I can cross off this side because when I find the pivot, right, I know 4, 5, 6, and 7, because this value is greater than what's on the right, what's on high, the pivot's not going to be anywhere here, right? You can see very clearly in this example that 4, 5, 6, and 7, because this value is greater than high, all these values are going to be greater anyway because the array is rotated. Right? If it was rotated one more, if your last value was 1, right, all the values to the left-hand side are going to be greater. That's why you can choose to keep doing that. Right? If it was rotated this way, it'd be the same story, right? All these values are going to be greater than all these values, right? And we want to find the one that's going to be the smallest value. So that's kind of the reasoning for that branch. I break this down to 3 branches because I found it actually extremely difficult to write it in 2 branches. This condition is the one that Ethan said, basically, right? With our current index, if it is less than the number that we saw to the left of it, then that must be our pivot, right? And if we ever find that condition, then we should basically break out of the loop. Okay, I'm gonna try not to like look at my notes now, just so that like I can be here on the Google Doc more. All right, so I think this is good. So if nums mid is less than nums of mid minus 1, right? Then we have found our pivot index. Because I plan to use the pivot, I'll use this right here. That's right. Pivot index, let's say I'm just going to initialize that to low. I might change that later, but it just needs to be initialized to something. So pivot equals mid, right? Because it's the index with the smallest element. I'm also going to break out of here. Okay. Now how should I cut the left and right halves? So this is our value, right? If the number at mid is greater than what we saw at the right, all the way at the high end, right? What do we want to do? We want to keep searching on the right half of the problem, or right half of the space. So we actually move low equals to mid plus 1. Okay? Now there's an else block. What happens in this else block? So close. So I moved low in the if block. So what does that mean? Yeah, I have to move the high now in the else block. Right? It's symmetric. Okay. So I believe that, so what I think about a lot of times, I don't know if this is completely correct, is that, oh wait, actually, do we actually need a less than or equals to case? That's what I'm thinking about. Actually, we don't, because we only ever have distinct values. So yeah, this comparison is fine, because you don't ever have to like care about greater than or equal to then or less than or equal to then. You can just use the bare greater than or less than comparator, right? Because all the integers are distinct. All right. So this is the way that we preserve the invariant, that we're always going to choose the half that is going to have the elements that are hopefully smaller than what we have at mid. Hopefully I said that right. This I would like to translate into actual Python, like running code. And I know we are shorter on time, and I want to respect that. It's already 3:25. I'm going to erase all my code. I'm going to pop this in here. And feel free to also try this yourself as well. So I'm going to just an invariant in the problem is something that it's a thing that gets preserved. It's a thing that doesn't change about the problem as we narrow the problem down to the solution. You'll see invariants talked about in this kind of problem, but also if you're familiar with greedy kinds of problems, they also operate on invariants, in that there's always a way to make a correct choice. One invariant to look at just in basic binary search is just like the numbers, right? and how they're ordered, right? Being sorted, right, guarantees an invariant, right? It guarantees that there's going to be a property preserved as we move low and high, cutting the values left and right, right? The invariant means is that we always will have an answer and always a way to make a correct choice to get to that answer. Hopefully that makes more sense. In this problem, in search rotated sorted array, we're maintaining the invariant that whichever half we're looking at, like see here, so if num's mid, this is the value, right? If this is greater than high, then we know that that the correct pivot lies somewhere in here. So, and we can keep cutting down the problem, right, further and further this way, with the same rules. Binary search can also be written by recursion. You don't actually have to use a while loop for it. And through each recursive stack, it's the same. It'd be written much the same way. You just care about the property that is preserved. So I'm just going to print the pivot. You can think of it like that. It's when the problem space that you shrink things down into is guaranteed to have a solution. So I printed this out and it says that our pivot is 4. So at least for this problem, it looks right. For case 2, well, it's the same input nums, so the pivot is 4. So that also seems correct. And case 3, the pivot is 0, which is, I think, also correct. Yeah. We will have to return something other than -1. So this is only the first part of the problem. That's actually the meat of the problem. So we determined where the pivot is, right? Now we get to use the pivot to find the actual target value, right? So it was a 3-step process that we're going through. First of all, let's find the pivot. Once we find the pivot, what we can do now is decide which half that we want to search in. And after we decide which half we want to search in, we can just use bisect library in Python. So that's the plan. There's actually a way to, I think, if you do this using only one binary search. I never came up with that way, but if you're curious, you can look at other people's solutions. They're like extremely concise. Actually, this person does use 2 binary searches. But yeah. You can see that in other people, they write binary search, they might use like low is less than high, but then it's not symmetric. You kind of have to figure out like, oh, low is going to be equal to mid or something, or low is mid plus 1. And I've personally had problems writing it that way, so that's why I stick with the template that I have. But same idea here, right? This person found where things are rotated. It just turns out that in their loop, like it converges, the value converges into low. So they just set the rotation point to low. Again, binary search is like tricky to get right, which is why I recommend using templates. You don't have to use mine, you can use someone else's. Just make sure that when you write binary search though, the less decisions you get to make, the better, because it is riddled with pitfalls, despite how simple it is. All right, so Yeah, the key part, like once you start using templates for writing binary search, you kind of have to figure out, well, first of all, you should figure out like how you're going to use that binary search. Without figuring out how you're going to use it, you're going to struggle with the implementation a lot. So anyway, that's the pivot. Now, given the pivot, can we write the rest of the code in order to find the target? What are we going to compare? Yeah, basically. Specifically, can you write out exactly what you're going to do in code, though? So let's look at this example 2 right here. We know now that the pivot index is 4, right? Let's just assume that the code for the pivot is right. Which half are we going to look at? Actually kind of like, I don't know. Maybe the right half? Yeah, you're right. I think it's the right half. Because you can look at, oh, this is 4 to 7, right? The value is from 4 to 7. We know 3 is not going to be between 4 and 7. We can look at the right half. But this is also between 0, 1, and 2. For the sake of like maybe a better example, pretend this target is 1. Yeah, you would pick the right half for 1. But how do we make that decision? How do we know 1's in the right half? How can we tell how would a computer know? Yeah, sorry, I spoke probably very confusingly. Now that we have the pivot, we have elements from the pivot all the way to the end of the array. And we have the elements before the pivot, right? I'm saying before we even do binary search, before we even do that, which halves should we use for binary search? Okay, that's only for this problem though, but how do you make that decision using code? Hold on, you just gave me an idea. So what you could do, so you're talking about like thinking about elements on the left side and the right side and comparing them to target, right? What you can do, if like you really wanted to, right? You can use one simple comparison to decide which half, right? Or you can just binary search both sides and see what happens. Sorry, repeat what you said? Yeah. So I think, let me just like Control Z. I'll show you how I originally solved this and how I thought we might do it, but it might be simpler to just to like not worry about this specific comparison. But basically there's two monotonic increasing sections, right? 0 to 2 is always going to be increasing. 4 to 7 is always going to be increasing, right? So you compare your target. Is your target less than or equal to than the last value? If it is, right, then you know that you can search on this half if there is an answer, right? But if 3 or whatever value happens to not be less than the last value, which is 2, right, then we know that like, well, 3 won't fit into this right half, right? So maybe it fits into the left half. Again, you can switch the logic around if you want. There's multiple ways to do it, so there's no like completely right way. But what we can do, actually, I can fast forward. Yeah, that's what we have. We can actually just use 2 binary searches. Like guess 1 is going to be actually the array. It's going to be nums. We're looking for target. The low is going to be from low to pivot -1, right? And guess 2 equals, you know, we can just do another binary search on the left-hand side. Right. So which index should we start with for this binary search? Okay, but how can we write that in code? It's actually going to be, it starts with a P. Remember? When we are, so now, okay, so I switched this up on you, so sorry about that. But basically, we're going to do binary search over here. So we're going to do a B search here, and we're going to do a B search here. Right? This is a binary search. I didn't have enough room. Yep, happens at pivot. That's the lowest possible index for the other one, right? And finally, the last index we can use, that's actually going to be length of nums -1. So so actually, well, okay, to be more specific, one of the binary searches bisects the left. The other binary search bisects the other half. So this is the left half, right? So that's 4, 5, 6, 7. Right? Because you go from low, oh wait, sorry, I need to like reset that to 0. For this problem, bisect left will tell us, so if you read the documentation, bisect left will give us the answer, like, will tell us, like, will give us the index if it exists, and if it doesn't exist, it'll tell us where to insert the index. Bisect right does something, I think, else. You can read the documentation. This returns an insertion point after which comes to the right of any existing entries of x in A. So this actually does different behavior. Maybe this could work if I changed my logic in order to fit this. But I know bisect left is going to work because it will actually give me, like, if x is already present, the insertion point will be before to the left of any existing entries. The return value is suitable for use as the first parameter to list.insert. But it'll basically when you do an insert, you would insert to the left of something, so it actually would give you the correct index of what it exists. So let's say if you were looking for 4, right? You would find this index. Well, if you wanted to index to the left of all 4s, it would just be this index right here, right? So if it exists, it gives you the leftmost index of it existing, which is why it works, right? If you used bisect right, you would get this index right here. And that's not what I want. I actually want where the value is. So read up on the bisect library, just learn some of the ins and outs. I'm going to try to just finish out this problem because this is a 142, and I think this is probably too long for what I hoped was a shorter lecture. Okay, so it's possible if guess 1 is going to be possibly greater than so if this exceeded, right, guess 1 is not the answer. So basically if guess 1 is less than pivot and nums of guess 1 equals target, then I can return guess 1. And it's much the same story for guess 2. And the reason why I do this is because bisect left is going to give us the first value, right? This could actually exceed the bounds. And if it exceeds the bounds, if guess 1 actually equals pivot, then we know that the value was not in this half of the array, right? So the guess must be less than the pivot itself, right? It has to be up to pivot minus 1. So it's the same guard here. It's the same concept. Bisect left could give us a value outside of the array. So it's only true if our number is within the array. There's probably a cleaner way to write it, but just to show you an example, this logic should work. Okay, and it seems to pass for those cases. I'm actually curious whether this is actually going to return the correct code. So I'm just going to submit this for us. And if it's not, feel free to debug it. But this is basically the crux of the problem. Use binary search, figure out where the pivot is. And based off of the pivot, you can now follow a binary search pattern. And hey, look, it passed. So what we did was right. So yay us. Yeah, so here's what happened. We used Ethan's insight about how to find the minimum element. We translated that in a way to write that into binary search, where we basically did the comparison, but also we had to choose the condition, right? The condition is maybe the most important thing about the binary search. It is what helps us decide how to winnow down the problem into smaller and smaller chunks. And we did that by using this comparison to give us the invariant that whichever window we're going to look at, we want to guarantee that the pivot is inside that window between left and right. Once we found the pivot, we were able to use binary search just on this half of the problem or this other half of the problem as well. Really though, before you submit, you should really test on smaller cases of what happens if the value actually exists and there's no left and right half, right? Because there's only one value, right? And what should happen if there's actually two values and we exist on the right half only, right? So those are test cases you should think about trying out before submitting. I kind of submitted just to kind of like help us wrap up, that's all. So we followed the template basically, but like I said, sometimes it's easier to like break things out into separate branches. For this problem, I found it extremely difficult to write it in just 2 branches using the other parts of the template. You might find a binary search that is a template that better suits your style or whatever. Feel free to go with that. All right, so, oh yeah, I wanted to get through this search and rotated sorted array too. I think you're ready to like try that one on your own. Obviously, it's very easy to write a one-liner for it, and you can just write this, and boom, you're done. But think about why the worst case cannot be solved in log n time. I've included some practice problems, and there's also a teaser for part 2 if you're interested, but likely we won't get to this for many weeks. And that's it for the lecture today. Sorry it was long again. But send me questions if you're struggling with doing some of these algorithms. And I'll see you in the next one.